Good afternoon and welcome to my presentation on the paper Metacognitive Calibration, a methodological expansion and empirical application. I'm really happy to be here today, also virtually online. My name is Tobler and I'm a recent graduate from the Professorship for Learning Sciences and Higher Education at ETH Zurich in Switzerland. To start my presentation, I would like to introduce the theoretical background underlying this project to explain why it's important to look at this. So, to start, we need a working definition of metacognitive calibration. And the metacognitive calibration, following Tobler in 1991, is the idea of a learner's ability to correctly judge their own performance. So, thereby, misjudgments mostly come from overconfidence, which indicates the wrongly thinking that own wrong performance is correct, whereas overconfident negatively influences learning by reducing the cognitive efforts for processing new information, as well as underconfidence, in other words, wrongly thinking that own correct performance is wrong, which in the end negatively impacts self-confidence, which impacts learning through affected intrinsic motivation, which also influences the ability-grounded failure attribution, and ultimately impacts learning. So, accurate metacognitive calibration is an influencing factor for successful knowledge acquisition in any domain. However, we need to ask ourselves, how can we reliably estimate students' metacognitive calibration? And there has also been some prior research done from Schraw et al. That was pretty fundamental. And their conclusions were that first, appropriate metrics depend on the research questions. I mean, there's not one metric useful for all the research questions, but this depends. And second, that one measure is only rarely sufficient to estimate metacognitive calibration. Instead, a combination of different measures might be as fruitful or as impactful for really knowing something about the student's metacognitive calibrations. Additionally, there are some statistic inherent limitations that we will discuss now. The first one being that mostly they look not at over and underconfidence, but just look at an overall calibration score. However, overconfidence and underconfidence are very different concepts as a student, and also they affect different learning. Second, they often do not allow between comparison, being due to standardization of the scores or other factors that influence whether studies can be compared. And lastly, statistics are often based on dichotomous answer patterns, meaning yes or no, or I agree or I disagree, despite students' more nuanced estimation of their own performance, and without any mathematical possibility for generalization, means there is no other option to increase or to adapt this measure to other than yes-no answers. So, no measure outperforms the others, and all measures entail substantial limitations for research and practice. And second, novel statistics are required for analyzing metacognitive calibration. And this is also where the aim of this current study comes in. In this study, we introduce a novel set of statistical measures for assessing calibration accuracy and the direction of miscalibration, indicating overconfidence or underconfidence. And also, we make a proof of concept study by applying the statistics on data, on a binary, and as well as on a 4-point indication of metacognitive calibration. Like this, we are not only able to validate the prior statistics, but we can also directly compare them with our novel statistics on the binary matter, like how they would assess it, even on a 4-point indication, whereas this more variance can be explained. So, our aim is to advance the methodological standards for determining and interpreting metacognitive calibration. And second, we present an R package to calculate and visualize calibration accuracy and miscalibration. So let's start with the methodological expansion of calibration accuracy and miscalibration. In the first step, we try to build a robust measure for binary systems that can be generalized. And to be able to develop such a system, we need to redefine over and underconfidence, or at least the mathematical formulas for them. And for this, I would like to introduce this table, in which you can see the performance, which can be either correct or incorrect, and the confidence judgment, which can be, for example, yes or no, or I agree or disagree, or I feel confident or I feel unconfident in a binary system. And what we have is we have a true negative, true positives, false negative and false positive values that can be selected by the students, which we will now depict as A, B, C and D for the future formulas. If we then look at overconfidence, that we saw to be frequency of which learners wrongly judge their answers as correct when they're actually not, we see that O, or the confidence, can be defined as the relationship between false positive over the sum of all negative answers. If we look at underconfidence in a second step, we see that this is the frequency with which a learner wrongly judges their answers as wrong when they're actually correct. So the metacognitive accuracy depends on these two measures. The accuracy value that reflects this must hence include high confidence, high underconfidence, high overconfidence, as well as the combination of these two, so O and U that we saw before, as well as their frequency of their occurrence. It's important that we include how often does it occur that someone is underconfident or overconfident with their answers. And lastly, it helps if we look at the inversion of this whole value, because then we have a full accuracy if we have C equals to 1, and we have complete inaccuracy if we have C equals to 0, which is more intuitive as a measure. We also need to look at the direction of the miscalibration. So the calibration accuracy does not make any statement regarding whether we see overconfidence or underconfidence. So we can, however, apply the same theoretical and mathematical reasoning for the second statistic that we see now. So the miscalibration M can be seen as the relative occurrence of false positive minus false negative values. And where an M equals 1 would indicate full overconfidence, M equals minus 1 would indicate full underconfidence. So a student with full underconfidence would have a calibration accuracy score of 0, but a miscalibration score of minus 1. So the advantages of these measures over the others are that they're not based on standardization. They're between study comparisons easily possible. And in combination with the calibration accuracy, we can assess the accuracy of the performance as well as the cause of any inaccuracy. So in the second step, we now look at the generalization of the developed model. And overall advantages of the statistics that we saw before were that there's the same underlying mathematical basis that allows direct comparisons. And second, that it's scalable to any dimension of interest, such also on quaternary datasets, including 4-point Likert scale data. For instance, if we look now at the table that we saw before regarding performance and confidence judgment, and we try to improve or enlarge this table for 4-point Likert scale data, we would end up with something like this. The students would be asked, how sure are you with your answer? How confident are you with your answer? And they would answer with yes, rather no, and no. So we have two more dimensions that we had before. So we also have double as many answer possibilities or combination possibilities for incorrect and correct performance. Now, the mathematical explanations how to get to these new formulas are a bit more complex, but they're extensively described in the supplementary materials of the paper. In this presentation, I won't focus too much on these different calculations, but directly present you the formulas. So as you see, they're kind of complicated. Additionally, you might realize that we have now x and y values inside as multiplication terms, and these are weighting terms, because we need to weight the answers differently, because otherwise we end up again with a binary system. So, having been able to generalize this whole model for calibration accuracy and miscalibration, we come to the last step, what we did. We developed an R package that can be directly implemented to any R environment, directly downloaded and installed, and freely accessible. So, since these developed statistics, especially for higher order, become quickly challenging, we developed an R package, including novel statistics like the calibration accuracy C and the miscalibration score M that we determined. We used the commonly used statistic like D, gamma, and G index that were frequently used or the contemporary used in research. And lastly, we added functions for visualization and simplified analysis to support researchers and practitioners in their analysis process. And this whole R package is an open source project that is freely downloadable from GitHub. So, as I said before, we also did an empirical application and proof of concept study. And for this, we recruited 34 doctoral students in natural sciences and gave them, after they indicated their participation and after the University Commission accepted the study, we gave them a reliable concept inventory on molecular stochasticity, which is a fundamental biological concept, and since they were all doctoral students in biology or related fields, they should have an understanding of this fundamental concept. We also gave them a confidence rating to each of these questions on a 4-point Likert scale and asked them, how confident are you with your response? And they could indicate as very confident, rather unconfident, or very unconfident. For the analysis, we calculated the novel statistics, the calibration accuracy and miscalibration, and visualized the findings. We also determined the conventional measures like D, gamma, and G index and compared these measures to the new statistics. What the study results showed were that the students understood the concept relatively well. In average, they scored 72% of the whole score. We also found that the average calibration accuracy was relatively high, with 84% or 0.84, means most students had a high accuracy. What we also found that the average miscalibration indicated a slight overconfidence, especially with lower calibration. And this you also see in the point plot over the violin plot, that certain points that are orange or reddish indicate lower calibration and they are even higher in miscalibration. If we compare these findings now to conventional statistics, we found that the novel measures results, as assessed on a 4-point Likert scale, revealed significant correlation with the G index and fewer correlations with other measures. Now, looking at the binary data, we found more correlations with the prior measures of the collected data. So, what this means is that the 4-point calculations contain more information that other measures cannot capture. And it also indicates that the novel statistics allow accounting for more variance and thus reveal more precise estimates. And this variance is also reflected in the performance-specific calibration analysis. If we split up the performance score and look just at miscalibration, we see that the performance score-dependent breakdown, we have a greater variability in accuracy and miscalibration with lower performance. And with this, we also come to the discussion of these findings. So these novel statistics, calibration accuracy and miscalibration overcome the limitation of commonly used statistics while still measuring a similar construct by explaining more variance and by addressing over and underconfidence. Moreover, the new measures are easily applicable, directly scalable from binary to 4-point scale ratings, or even generalizable beyond that, and allow between-study comparison of metacognitive calibration. Lastly, the additionally developed and freely available and directly implementable R package allows applying the novel measures as well as the conventional statistics and facilitates calculation, visualization, and interpretation. These are the references that were used in this presentation. A more extensive list can be found in the paper itself. And with this, I'm at the end of the presentation. I would like to thank the conference chair for having made it available that I can still present despite not being physically there. And I would like to thank you for your attention to this presentation. For any question, do not hesitate to write me an email or contact me in any other way. And there are the links where you can find the paper and a link also to the R package to try it out on your own dataset. Thank you very much.